This lab is Lab 11, which is associated with Lecture 11 on logistic regression. And it will be a pretty short lab today, but I just want to show you some of the basics of running logistic regression. And we're using our favorite iris dataset. I promise we'll abandon this and never use it again, hopefully, after this lab, I think. So again, I'm going to subset down into species, sepal length, and width. Although I encourage you to play with this, with this data set with other variables there too. It's just obviously for visualization purposes, easiest to visualize it this way. And I'm going to also just look at two of the species, the versicolor and virginica species. And the reason I am going to do that this lecture is because logistic regression in the most basic case is just a binary classifier. So one or the other. So we only want to look at two classes to start off with here. So I'm just going to use, I'm going to kind of get rid of that out of my data set. I'll set all the setosa to NA, and then I'm going to remove, re-level my factor here. In fact, I think I'm going to, well, let's see. So yeah. Oh, right. So what I do is I first in this line here, I subset down to just versicolor and virginica. You do have to remove. You still have to remove it from a factor because so let me just do this in a couple stages here, and I can show you what happens. Is that if I run this and okay, it looks like I've just looked at the subset of the rows of my data set that have things that have flowers that are either virginica or versicolor. It looks like it's all good. The problem is if I look at my species, and maybe I make a table of the species, it still thinks it's a 3-level factor. It just thinks one of the factors has nothing in it. So it says 50 in virginica, versicolor, 0 in setosa, and that can get confusing. So what I do here is I remove my setosa, and then I change the reference level. So this function re-level will change the reference level to versicolor. And if we get a little time at the end, we might look at that in more detail. But so after I do this, I can now I have just two level factor here. So the function that we use for fitting logistic regression is called GLM. And so this seems a bit strange. This is a generalized linear model, but one of the reasons that logistic regression feels like a regression method, and why it ultimately was named logistic regression, is because it's part of a family of what's called generalized linear models. So simple linear, or just linear regression, as we learned it back for a first regression technique, is obviously one of a generalized family of linear models where you're predicting continuous outcomes. If you want to predict binary outcomes, you get what's called logistic regression. There are also other types of regression, Poisson regression, if you want to predict counts, and then there are other types of models there. And this all ties into kind of they're part of what's called an exponential family of distributions. But GLM is a kind of generalized version of regression. You can actually do a normal regression using GLM. But the way you specify what kind of regression, what you do is you specify this family. So Gaussian will give you a kind of classic regression, and if I want to fit so let's just skip through most of this. It's a little too much detail, but if I want to fit a logistic regression, I'm going to use what's called a binomial family. Let's go all the way down here. Okay, so if I want to fit my logistic regression model, I'll call it log mod, I'll use GLM. My formula is very similar to a normal regression model. I pass in my data, but now for my family, I pass in binomial. So here, binomial is obviously a generalization of Bernoulli. So in lecture we talked about how basically we're fitting a Bernoulli model. For one reason or another, they call it binomial in the software, but you can think of it as Bernoulli. And so that tells me I have a 0-1 model. I want to use a binary model, which is logistic regression. So that is the the generalized linear model for binary counts is called logistic regression. So I can fit it that simple, that's what it is, and I fit it, and I can even summarize what's going on. So if I call summary on my mod here, one of the reasons it feels so much like a regression model and why it's called logistic regression is you get this whole coefficient table. Just like in a regression, a normal regression case, I'll get my estimates of my intercepts, my betas. The betas have a slightly different interpretation because they're now like in an exponent in our model rather than just on the linear scale. And I get standard errors, I get p-values. So much of the statistics from the classic kind of Gaussian family linear modeling definitely applies to generalized linear models and in particular logistic regression. So you could take a whole course on this, and if you were a biostatistician, you would take you talk about this in a lot of detail. So one of the reasons people love logistic regression is because it's incredibly interpretable, which is an underrated skill, but underrated feature. It's interpretable, has coefficients you can interpret in various ways. But we're not going to get too much of that in this course. In this course, we're mostly focused on prediction. But prediction is not the whole game, right? Sometimes you really do want to understand what your model is doing. You'll see here at the bottom, although it's not too important to us, it says number of Fisher scoring iterations. Number of Fisher scoring iterations. If you remember in the lecture, I talked about, and just very briefly talked about, how logistic regression was fitting through a maximum likelihood estimation procedure, and that there was unlike kind of classic regression, where we had this closed form x transpose x, inverse x transpose y, etc. There is no closed form estimate for the betas we get here in our logistic regression. These are gotten through an optimization routine, in particular a gradient descent routine or ascent routine. And so this number of Fisher scoring iterations is related to, I'm not sure it's exactly the number of iterations, but it's related to the number of iterations we do in our maximum likelihood estimation. So here, Fisher scoring, if you take in 452, this is a somewhat meaningful phrase, or suspiciously meaningful. It's related to the Fisher score, or information and information related, but it's basically the gradient of our the gradient is called the score of our function that we optimize to get these betas. Okay, so that's just a little aside there. But so we get our estimates, and then R makes everything nice and easy for us. So we could say predict, and if I call predict here, we get kind of a weird output, right? So this is neither the class labels, right? The class labels should be what? Virginica or versicolor, right? Nor is it the probability that P sub beta we were talking about. It's not the probability of being class 1. So what is it? So if you remember when we looked at what was our model said that, let me actually just write this here. So our model said that P was logistic of x beta. It was something like that, right? So this was our model. And let's say, I can still remember how to write in tech. This is equivalent to saying that x, let's say, logit of P is x beta. So our model these probabilities of being in the one class over the other as this logistic function of our x times our beta. This is the equivalent, our logit function, which was the inverse. If we applied it to both sides, that would say the logit of P was x beta. Well, the logit of P is, I think we said, is log of P over 1 minus P. well, let's see if that renders. Yeah, that vaguely renders correctly. So logit is just log of x over 1 minus x, right? Or logit of p is log of p over 1 minus p. So what it's giving us is actually this logit, or so-called log odds. It's giving us x beta. It's so you could actually calculate that by taking your design matrix and multiplying by beta, and that would give you these. So that's what we're getting here. We don't need to see as many of these, so let's just look at the first couple of these. So theoretically, we should be able. This is a little dangerous here. So this is my model matrix, and this thing is what? How big is this? Should be about 100 on one side, 100 by 3, okay? And my coefficients, my beta hat, so what I'm claiming is that the thing is x beta hat, should be, that should be beta hat. And really I want to make this this thing was 100 by 3, right? 100 rows. Just look at the first couple of these rows. 100 by 3. I really want this thing to be 3 by 1. Is that what I want? Then I would get 100 by 1, which would be the correct dimension. Okay. So this is my beta hat. So presumably, let's just call that x design. Something like that. If I presume that if I take x design and I multiply by beta hat, we did something like this back in one of our first labs. So let's look at these. 1.565, 507, 0.42, 1.3, 1.56, 0.42, 1.3, right? So this is exactly x beta that is giving us back. Of course, we probably, I mean, you can do things with log odds. We probably want to actually predict the classes. So you could try, there's another argument you could give to this called response. Unfortunately, it won't predict the classes for us, but it will predict the p-hats. So this is the p-hats, and these are all between 0 and 1. So these are the p's. So this is, so if we give a response, it'll give us our p-hats. If I, my claim was that the straight up predictions were log of p over 1 minus p, so we can actually look at that, and indeed, they are the same. So these p-hats are equivalently, you could do the logistic transformation and see that if you take the log odds, throw it in the logistic, you get the p-hats. In any case, these p-hats are probably the most useful because it will allow us to predict the class. So one thing I can do is I could just say which of the p-hats are bigger than 0.5, and I multiply by 1 just to make it numeric. The alternative, which is less of a hack, would be to do this. This just tells me which of my p-hats are bigger than 0.5. The things bigger than 0.5 should be class 1. If you remember way back up here, back when I re-leveled this thing, I said the reference level was versicolor. So that should be the zeros. So if I look at, this is not going to play nice, is it? Oh no, I broke it somehow. That's not good. But let's just rerun our stuff. Huh. Let's see. So versicolor, I guess, is 1. So our reference levels are 1. Just got to check that out. So our reference level is 1. So versicolor is 1. Presumably, if I looked at the tail, then Virginica would be 2s. Okay. So that's the way it's coding them. So it's coding versicolor as 1, which is our reference level. This is a useful idiom to know here, because you have to pay a bit of attention for this for logistic regression. And our other ones are versicolor 1s for Virginica 2. Okay, so we go back down, down, all the way down here. Back to here. Okay, so 0s should be our reference level and 1 should be our second level. So we said versicolor, right? Oh boy, I'm already forgetting. Let's just check real quick. Our reference level is versicolor, so that should be the first one. So, oops, let's not skip here. So our labels are versicolor and Virginica. So the versicolor, we now label them. We turned this thing into a factor instead of 0s and 1s because that's confusing. You just have to make sure you get it correct. So our base level is versicolor, which should be the 0s, and our second level is Virginica, which should be the 1s. So you can always use, say, our caret package. You can look at the confusion matrix. Yeah, it does okay. Accuracy about 0.75 with no fiddling around. This is obviously training accuracy, so all the caveats that come with that. But so in order to actually get, for using GLM, in order to actually get our predictions, we have to look at which of the, you can get the p-hats, which are bigger than 0.5, and then you turn them into a factor. And you have to make sure you get which is 0s, which is versicolor, and which is 1, which is Virginica in this case. And we can use our favorite plot function, some slight additions here to do the prediction correctly, with our plot mod function, which we've seen before a couple times, to plot these, and we could just plot our logistic regression model, and it would look something like that. So our training, this is obviously just for the training data, but here would be the split learned from this training data, which is on the left. Here we have our versicolor, and the right in Virginica, and that vaguely lines up with our training data there, although they're a little hard to separate. Versicolor and Virginica are pretty hard to separate there. This doesn't look like it, but this is a line, right? So I said it's a linear classifier. This is a line. It's a little bit rough. Maybe I could increase the grid. This is going to take forever. There we go. So that's, increase the fidelity of that grid there. So that thing is a line, right? It's a linear classifier, which is what we claimed. And we know it's a linear classifier because of all that math I did. If we go back up here, right? If we look at we just can throw this thing into this. These are basically discriminant functions, and we get, if you throw into logistic or the logit function, you get something linear in our design matrix, this x beta here. Cool. So that's cool. Of course, we might want to do what is called multinomial logistic regression, which we did real quick. And so I can, I really have 3 species, right? So let's actually just let's move this down here. Right. We have 3 species, those are versicolor and Virginica. So we probably want to fit a multinomial. We might actually want to do a multi-class classification, not just binary. This package nnet, which I believe is a neural net package, can do this for us. So there's some deep connections between neural nets and logistic regression. So you don't really understand neural nets until you understand logistic regression, in my opinion. Although lots of people don't understand logistic regression playing with neural nets. So we can build this nnet package. Has this function called multinomial log linear models, which is another way of saying logistic regression. And we can fit this. So it's even simpler. Actually, it's a much nicer interface than the GLM package. So fit this, pass in their new data set. Our data set 2 has all 3 classes. And so, for example, we predict when you call this, we're going to be able to call a summary on this. Let's just try that. So yeah. Okay. So when I call this in the fitting, you see it has the iterations, right? It's doing this gradient ascent to find the maximum likely estimator. So that's what it's doing here. I guess it does about 100 iterations here. Here's our summary information with some coefficients, etc., that you can interpret. Similarly, there's a little bit more going on here, and then we get our predictions, which look to be pretty good, right? You can see the setosa here are correctly, and the versica and virginica are harder to separate. We can modify this plot mod function, which is actually much easier because I don't have to mess around with seeing which is bigger than which, blah, blah, blah. I just call predict, and I ask for the type class, and that will predict. Let me actually go back here. So if I do predict, what is this thing called? Mod 2, right? So the default is class. I think there are some other types. Class probs. So if you ask for probs, it's going to give me probability, the 3 probabilities, right? And all my Bayes classifier does is it just picks the one that's the largest, right? So the setosa is very certain, our setosa. Of course, this is training error, so it could be a little overfit. And then you get versica and virginica, and it has a little more trouble. So it's definitely not setosa, but we're not really sure versica or virginica. And, if I just apply to each row of that prediction matrix of the probabilities and find which is the maximum, that just gives me my classes. One here, my class predictions, one being setosa, and then of course, we have our 2 and 3, which are versica and virginica. Okay, we're almost at time here, so let's just say we can also modify this plot mod function, which we said before, and we could do a nice little plot of this, which of course gives us now a 3-class classification. Again, we see our setosa separate nicely from the other ones. This is linear, and these boundaries are linear. Of course, we could increase the fidelity of this thing. Let's just do it a little bit so we don't have too much computation. And let's do a prediction. So these are our linear boundaries between our classes, which is kind of cool. Of course, with all of these, right, I can, it's only linear in, of course, my kind of design, the space of my design matrix. So if I want to do something more complicated, and I could say, look at the interaction between sepal length and width, you have nonlinear boundaries here. It's not too interesting. What else can we do? We can make it probably more interesting. Let's look at the square. Let's add on a squared term. That can be more. Yeah, so we're getting kind of some weird boundaries here. But again, technically linear, but has a lot of flexibility because it's just like regression, technically linear. You can add on covariates and make it really interesting. Okay, so let's stop there, and that's a nice quick overview of logistic regression.